The modern e-commerce standard is built on a massive assumption, a persistent, high-bandwidth connection. In the traditional thin client model, the front end is little more than a visual shell. Every time a user clicks Add to Cart, the app fires a synchronous API request, waiting for the server to validate and record the action. When a system relies on a continuous round trip for every interaction, the network becomes a single point of failure, turning transient lag into a total application freeze. In e-commerce, a dropped connection at the moment of intent translates directly to lost revenue. When a transient network failure disrupts a customer's action, the resulting friction almost always leads to irreversible cart abandonment. The intent is discarded simply because the network blinked. To neutralize this failure mode, the traditional client-server relationship has to be inverted. Instead of treating the front end as a dumb terminal, the local device must become the primary source of truth. Every read and write transaction executes directly against a local storage layer. Under this model, the centralized server is stripped of its role as the immediate gatekeeper. It is relegated to a replication target, a system that quietly syncs state in the background when connectivity allows. Designing a highly available distributed system requires treating network connectivity as a highly variable state, rather than a constant guarantee. By completely decoupling the user's intent from server-side validation, the system can capture, persist, and safely process transactions regardless of the network environment. This offline-first architecture requires a stratified client stack, beginning at Layer 1, the local database. To guarantee sub-millisecond responsiveness independent of connection status, all application data operations must occur locally. Looking at this data table comparing browser storage layers, you can see the boot overhead metrics for different solutions. WASM compiled SQLite takes a 504 millisecond initialization penalty to process tables on startup, while IndexedDB loads natively with negligible overhead. That 500 millisecond delay disqualifies SQLite for this specific use case. It blocks the critical rendering path, preventing immediate user interaction upon app launch. Local storage is similarly disqualified. While it has zero boot penalty, it relies on a synchronous execution model that blocks the main browser thread, and it is strictly capped at around 5 to 10 megabytes of storage. That leaves IndexedDB as the optimal persistence layer. It provides asynchronous, gigabyte-scale storage that won't block the UI thread. By wrapping it in an ergonomic transaction library like Dexy.js, developers can manage schemas and relational state efficiently on the client. Within this local database, we construct a durable outbound queue. When the device is offline, user actions like adding items to the cart are stashed here as durable operations, accumulating safely without freezing the interface. To manage this queue, the schema incorporates an isSyncOnline Boolean flag. Every new order starts with this flag set to false. It only flips to true once the background worker confirms the transaction has successfully reached the server. To prevent duplicate transactions when the network stutters and retries, every operation requires a client-generated item potency key, such as a UUID. The server uses this key to recognize and discard duplicate packets. By combining IndexedDB's asynchronous capacity with exact tracking flags and item potency keys, the client safely captures and locks in user purchase intent. The user moves on, completely independent of server confirmation. Sitting directly between this local persistence layer and the external network is Layer 2, the service worker. This acts as an embedded proxy layer inside the browser. The service worker ensures the application itself remains accessible during outages through a dual caching strategy. It uses a network-first approach for the application shell's HTML to capture layout updates when possible, falling back to a cache-first strategy for static assets like fonts and promotional images to guarantee the UI renders instantly. During an offline state, the service worker physically intercepts outgoing API calls. Instead of letting them drop into the network void, it reroutes these payloads, appending them as mutations into the local IndexedDB queue. Recovery is handled by the browser's native background synchronization API. This system registers a one-off task that lies dormant until the operating system detects a stable internet connection. Because the service worker runs in an entirely separate thread from the DOM, this background sync executes independently. It will successfully fire even if the user has closed the application tab entirely. When that connection is restored, the matching service worker listener wakes up and drains the local queue. It pushes the stashed mutations to the server sequentially, maintaining strict transaction order to preserve the exact sequence of the user's intent. Isolating all network communication into a background service worker decouples the user's perception of speed from the actual availability of the network. To the user, every action is instantaneous. Caching in queues solves single-device persistence, but a critical failure scenario emerges with multiple devices. Imagine a user offline on their mobile phone adds an item to their cart, while simultaneously logged into their desktop online, they delete a different item from that exact same cart. Standard conflict resolution strategies fail here. As this dual timeline shows, if we rely on a last write wins timestamp merge, the later online delete event at T2 blindly overwrites and erases the offline add intent from T1. The result is pure data loss. We need a mechanism that guarantees deterministic convergence across decentralized nodes without relying on a centralized server to coordinate and lock the databases. Modeling the cart using a conflict-free replicated data type OR set solves this. Adding item E generates a unique tag T in set A, tracking specific intent. Removing it moves its tags to a removal set R. Subtracting removals from additions deterministically isolates active tags. To manage the quantities of those active items, the OR set is paired with nested positive-negative counters. These PN counters separate increment and decrement operations, accurately tallying final item quantities even when multiple devices adjust the count concurrently. Together, these structures ensure that all state transitions form a joined semilattice. The operations are mathematically commutative, associative, and idempotent. Applying joined semilattice mathematics to a shopping cart neutralizes the synchronization problem entirely. Because the operations are commutative, the order in which packets arrive from the network is completely irrelevant. The math guarantees an identical, conflict-free state resolution across all devices, regardless of network delays or disjointed timelines. While the client side successfully captures and merges user intent, that data still requires authoritative business validation. We have to pivot to the server. When the background service worker finally pushes the offline queue, the server ingests the localized CRDT payload and maps it directly into a high-speed Redis hash cache. This allows for sub-millisecond lookups during active multi-device sessions. Pushing this validated state back down to active devices presents a severe human-computer interaction challenge. If background updates apply instantly to an active screen, items randomly appear or change quantities, causing layout shifts that disorient the buyer. To solve this, the application enforces optimistic UI with action-triggered reconciliation. If the user is just browsing general catalog pages, background changes from other devices update silently, subtly adjusting notification badges without interrupting the layout. If the user is actively viewing the cart page, the system enforces a frozen session state. Incoming device syncs are paused and held in a local staging buffer, freezing the active UI to protect the immediate interaction. The staging buffer is flushed and the UI updated when the user initiates a validation action, like clicking a checkout button, altering an item quantity, or refreshing the page. This protects high-friction transaction funnels from jarring visual interruptions. This careful orchestration requires centralized validation to be decoupled from the local add-to-cart action. The local device tracks structural variables, like identifiers and intent, not authoritative billing states. Final pricing, promotional eligibility, and absolute stock quantities are validated at the exact moment of sync. The backend cross-references the cart against an event-driven inventory engine backed by Apache Kafka, immediately reconciling the request against multi-channel point-of-sale data to prevent overselling. Offline-first design operates as an upfront constraint, dictating the technical requirements of every layer in the stack, rather than serving as a feature added at the end of development. IndexedDB provides the local speed, service workers abstract the physical network, and CRDT mathematics resolve distributed conflicts without needing centralized supervision. By aligning these specific technologies, the architecture neutralizes the chaos of absolute network unreliability. It shields the user from connection failures, preserves exact transactional flow, and ultimately protects merchant revenue in any environment.